Welcome back to ECE 441A, 541A. Your pre-quiz is due on the 5th, as are other dates that we were talking about before. Homework number 1 is due a week from Monday. Is that true? On the 10th. And how many show of hands have already watched the Lab 1 video? Just curious how anxious you are to watch that. It was posted yesterday afternoon, not that you have to, but it starts talking about how do you actually find a transfer function from experimentally obtained measurements. How do you excite a system, measure the response, and then determine what the transfer function g of s is for that particular system. That's the idea, or that's the concept behind lab number 1. And right now I don't have any sign-up sheets or anything, so let me figure out how we'll do that. But we may pass something around in class. We may then randomly assign some of the online people to various groups in the class, and we'll figure out how that will happen. Exam number 1, review material is now available. I thought I would get you ready for the long weekend. If you want to kick back and start really hitting the books, you now have lab 1 material to look at, exam number 1 material to think about, and homework number 1 is obviously due shortly after the long weekend, which I hope you're able to enjoy. Today, what I want to do are a few things. One is we'll sort of put things maybe a little bit out of sequence. Let's jump back and talk about finding a transfer function using block diagram algebra. And then we'll pick up where we left off on last lecture with this mechanical system, this 3-mass system. We'll review how we end up with these equations of motion. Hopefully you get comfortable with how we're finding these forces. Why is it z4 prime minus z2 prime and not z2 prime minus z4 prime? I want you to feel comfortable finding those equations of motion. Then we will look at putting all of those dynamics into a state space representation. Once you have it in a state space representation, now you can do all sorts of analysis, design in MATLAB or using any other state space based design or analysis tools. And that's why it's nice to be able to package any generic system into a state space representation. And we'll see if we can get that finished up today. Here is a classical block diagram configuration with our system in the forward path, some additional dynamics in the feedback path, and what I want you to do, just to sort of limber up your fingers and your brain, is derive the transfer function between the reference input R and the output Y. I'm looking now for this ratio. Assume that the output is single. It's a single output and it's also a single input. R is a scalar signal. Y is a scalar signal. I want you to now find the ratio Y over R from that block diagram. Take a couple of minutes. It shouldn't be too long to make that happen. And since it's not an exam, you can work with others if that would make you feel better. On an exam, that won't be the case. And if you're at home, you can bring in your mom and dad or brother and sister, and they can work with you on deriving this transfer function between the reference input R and the output Y. Did everyone come up with an expression for a transfer function? Did you obtain g over 1 plus gh? That's actually what, it's in the fall semester, it's a Friday, it's before the game. This is our second cheer of the semester, right? We have the A, B, C, D cheer. That was cheer 1. Give me an A, give me a B. Do you remember what that gave you? The transfer function in terms of state space representation, C times the quantity Si minus A inverse B plus D. That's what you'll scream out if somebody says, give me an A, B, C, D. Here, somebody might say, give me a G, give me an H, then you give them G over 1 plus GH. That you should just sort of, this should be second nature early on in this semester. If you see this block diagram, you now know the transfer function between the reference input R and the output Y is G over 1 plus GH. And one way to start doing this is to work with the signals coming out of summing junctions. That usually is a good way to start eliminating this result that sometimes happens as you feel like you're chasing your tail. You just keep circling and writing equations and you're not getting anywhere. But essentially what you want is you want one equation that contains only the reference signal R and the output signal Y, and you want to now solve for the ratio of Y over R. I'm going to offline show the details of that. How many actually found G over 1 plus GH? So a few of you. Is it okay if I do it offline after class? I'll try to record something and try to tell you how I would maybe go about finding this transfer function. The other thing that I want you to be thinking about is once you have that in your brain, this G over 1 plus GH, do you see how you could quickly find the transfer function for this block diagram? Here I might say you have unity output feedback. Do you understand where those words are coming from? Unity, that's 1. What's H of S? 1. So, and it's output feedback. And typically we just assume it's negative output feedback, the negative sign there. Here, in your G over 1 plus GH cheer, H is 1, and what's capital G? It's the product of that cascade or that series connection of two parts. D might be our controller, G is maybe the plant. Now that G is DG, so you have DG over 1 plus DG. Boom, you're done. Just by remembering cheer 2. Now when you get into things that are a little bit more, is this much different? This block diagram, you just have a pre-filter, don't you? A pre-filter of F, but you might see this called a 2-degree of freedom controller. You have a controller D and maybe a pre-filter controller F. This is now DG over 1 plus DG, but all of that gets multiplied by F. So you now have dg sub p f over 1 plus dg sub p. All of these should just start rolling off, but this one might not. Why? Because now we have a couple of summing junctions. But I'm just trying to show you that there are more than ways to connect or interconnect systems into block diagrams. But you want to start getting comfortable deriving these transfer functions between a reference signal R and an output Y. In this one, we actually have a feed-forward controller in the form of D sub 1. It goes directly, it feeds directly forward from the reference input R into the input signal of the plant, G sub P. And you also have a piece, a controller D, that's working on the air signal. If you labeled this as E as your air, and there's maybe U as the input, even if you start having all of these different labelings, the end result, your transfer function, better not contain any signal transforms. It better just contain D, D1, and G sub P. You shouldn't have any U or E floating around in your transfer function. Although they look the same, they're all capitalized. These labels and on the systems or subsystems and the signals are different. And you need to make sure that you're clear on that. G sub P is a system, subsystem. U is a signal. We have signals and systems, and you have to make sure that you're keeping all of those straight. All right. Block diagrams were finished for a little bit, but you need to start thinking through those all semester. You need to start feeling comfortable with working with block diagrams. Now let's go back and see if we can become comfortable with mechanical systems and finding their equations of motion and then subsequently putting them into a state space representation. Here's our process. First we sketch the system, and you know what system we're dealing with. It's that 3-mass system that we looked at last time. You need to identify the variables, and what was our sort of maybe more interesting variable that we had to identify in the 3-mass, that Z sub 4, that point between a dash pot and a spring. But once we had that, is the reason why everybody's still kind of low-key is because we're still in the reflection and meditation lighting in the studio. Do I need to up the light, or do we feel good about this? I just now realized I was going to change that. What do you think? For those of you at home, maybe you're still in bed with a little light on watching this. Basically, that's what's happening here in the classroom. Lights on. Wow. So much for reflection and meditation. Is this okay, or do you want to go back? I wanted to see your bright, smiling faces. Yes? No? Okay. All right. I kind of like, well, I don't know. I like both. It's kind of nice having a change. Maybe halfway through we'll go, no, then you'll go to sleep on me, huh? So we sketch the free body diagrams for each of those identified points. Then we write the force relationships associated with the free body diagram. And then we do our equation writing via equilibrium equations and substituting in the force relations. I'm going to quickly scroll through this because I want to get to the goal of today, and that is to put all of this into a state space representation. I'm hoping you don't necessarily have to re-sketch this diagram, but I have done one thing. I've relabeled my inputs as V's. So keep me honest. If a U slips in there, U is going to be our input vector, and it's going to consist of two inputs, a V sub 1 component and a V sub 3 component. When I was writing this, I thought maybe I need to make sure that we're not getting too confused by overusing U's and U1, U3. Here's free body diagram number 1. And I've received questions about, well, how do you know which way the forces are directed? And once you've sketched the free body diagram, or basically the mass or the massless points, then you start worrying about what forces are present relative to that mass. And the way that I'm using the inertial force, that always takes care of mass times acceleration. If we have a mass, if you try to push it in the positive z1 direction, what's special about z sub 1's direction? Anything or nothing. Something or nothing. Two options. Does it matter how I've directed z sub 1? Maybe that's a better question. No, it's arbitrary, isn't it? But once I've selected the direction of z sub 1, and now z sub 1 is 0 unless it becomes positive or negative. I'm assuming my system is in equilibrium, and then I label it. I put all the marks on the floor, and then I start kicking the system. And then it shakes or moves relative to z sub 1, z sub 2, etc. And if it goes to the right, then z1 will be positive. If it goes to the left, z sub 1 will be negative. The signs will take care of themselves. We've now arbitrarily established where z sub 1 is in this free body diagram. We know it's mass 1, and we know if we go in the positive z1 direction, if you tried to push something, an elephant, is there a force that sort of resists that push or movement? Yeah, which way is it directed? Opposite to the way you're trying to direct it, correct? So that's why F sub I sub m sub 1 is going to the left when z sub 1 is going to the right. That's the inertial force. That's the inertia of the mass that's trying to resist movement in the positive z sub 1 direction. That's why it's directed to the left. We clear on the inertial force. Now if I say inertial force, you're going to be thinking elephant, aren't you? That's okay. At least you start remembering directions, maybe. What about all of these other forces? What about v sub 1? That's the applied force. Can we do anything with its direction? No, that was given to us. We have to use the direction that it was assigned. And it could be in the same direction as z sub 1 or opposite, but we just have to leave it however it was given to us. That's the externally applied force, v sub 1. We don't change that one. Now what about spring k sub 1? If I move mass 1 in the positive to the right, in the positive z sub 1 direction, what's K1 going to do in response? Now just pull out a virtual spring or a physical spring and say, oh, if I tried to pull the right-hand side of that spring to the right, what's happening in my right hand if I have that spring? There's a force opposing that, and that's F1 sub k sub 1. And it only depends on the one end, the right-hand side, because the left side is fixed. It's an immovable mass. And we're just worrying about the spring force, which is dependent on the elongation or contraction of that spring. If we pushed z sub 1 in the negative direction on that spring, which way would the force be? To the right, which would really be opposite to how we've drawn it, but that would be consistent, wouldn't it? It would be a negative F sub 1 sub k sub 1, because we would be moving z1 negative. If that confuses you, just stick with what we just talked about earlier. What about one more of these, F sub 1 sub k sub 3? Why is it directed to the left? It's on the other side of the mass. Why is it in the same direction as k sub 1? If you now move that mass in the positive direction labeled Z1, what's K3 doing? It's going to want to oppose that movement, so it's trying to push left. So now you've labeled that spring force on K sub 3 to the left as positive. You now need the expression that involves the length, the expansion or contraction of that spring to give you a positive force to the left as you've now defined it in terms of Z sub 1 and Z sub 3. And I like to maybe just fix one and let the other one vary, fix the other one, let the other one vary, and see if I have my signs right. In this case, if you fixed Z sub 3 and you made Z1 more positive, would the direction of the force be positive the way that you've now labeled it and assigned it? Now we're saying that that would be K sub 3 times Z sub 1 positive. Is that true? If you fixed Z sub 3 and moved in the positive Z1 direction, what's going to happen to that spring K sub 3? It's going to want to push you to the left with a value equal to K sub 3 times Z sub 1. Is that clear? What happens if Z3 moves exactly the same distance as Z1? There's no force there, so that force expression better give me 0. That's where we get the Z1 minus Z sub 3. If Z1 moves exactly the same positive amount as Z sub 3, then you subtract those and you get 0 displacement of that spring, and there's no force. That's one way of thinking about where did this Z1 minus Z3 come from. Are we okay with that? And the dash pots are consistent with the springs. It's just that they produce a damping force that's proportional to the velocity of our masses. So if you could imagine maybe a shaft rotating in some heavy viscous fluid, the higher that velocity or rotation of that shaft, the more frictional force it's experiencing. Similarly, we're sort of viewing this as a mass moving in air, and as the velocity increases, it's being damped more and more. That's what the dash pot is like. And you might just watch the first minute of the video, Lab 1 video, and you can see the system, and you can see our little cylinder that's a tube, a clear acrylic tube. So you have to be careful, don't drop anything on it. But it now dissipates energy as the mass moves left and right. But it's then proportional. That energy that's removed from the system is proportional to the velocity of that mass. Here is a coupled second-order differential equation. It couples Z1, Z4, and Z3 because those are the other connections that are made with that system. Questions on that? As far as where did this set of equations come from? Really, we're just saying all of the forces going to the left equal all of the forces going to the right. And what are the forces? Well, we've figured those out by our force relationships of springs, dash pots, and masses. Question?
So I get that some of the forces in one direction equals to the U1 force applied in the other direction. For the differential equation, is that V1 or is that U1 on the other side? Is that representing?
Oh, thank you. I knew that I wouldn't catch all of my changes halfway through writing that. The question was, why do you have a U1 and a V1? I shouldn't. I should just have one externally applied force. Don't let me go that long again without correcting my notes. So that's V1, and it's the same V1 in the black box. That's the externally applied force. Thank you. Sorry. Sometimes you learn more when you make a mistake, right? Whenever I'm programming and it doesn't run, I go, good, now I really have to go understand the code. If it runs without an error, I go, I wonder if it's giving me the right answer. But you guys know how to make tests anyway. We move on. Did that help clear up the confusion, which I, not intentionally, but I did introduce by the labeling? Free body diagram 2. We've seen this before, so I'm not going to spend really much time on it. There's only one dashpot attached to that, so we have the dashpot force and the inertial force. They're both in the same direction. They're both on the same side of the equality sign. There's nothing else that those are equal to, so those have to now behave dynamically according to that differential equation. And in this equation, we simply have z sub 2 and z sub 4, but there is coupling with the rest of the system between mass 2 through z sub 4. Because if you look at this, if somebody was there and they were being ornery and they started shaking m sub 2, do you see that that would start trickling through everywhere? If we just had V1 and no V3, everything would still be shaking, wouldn't it? It might just shake differently. Free body diagram number 3, or for mass number 3. Have a little bit more going on. Here, note that the externally applied force, V sub 3 is in the same direction as all of the other forces that respond or appear when we try to move mass m sub 3 in the positive z sub 3 direction. Meaning v sub 3 in this set of equations is actually on the same side of the equal sign as all of the force expressions. And we end up now with a z3 double dot, or a z sub 3 double prime, the acceleration of mass 3, coupled with z1, and it's influenced by the externally applied force v sub 3. And these should all be consistent, although the last lectures we probably used u's instead of v's. But hopefully today I'll try to be consistently using v's as my components in the input vector u, if that can be any more confusing. And here was our potential source of difficulty, which concerns the massless point, and that was between a dashpot and a spring, and those are then the only two forces that are active relative to moving this point in the positive z sub 4 direction. And we simply then say, oh, those two sum to equal 0, and what are those two forces? Well, one is associated with damping of the dashpot b sub 2, so I have velocities impacting that equation, and the other side, or the other force, is a spring. Questions on those? What we want to do now is put all of these equations into one state space representation. We want to create a state space representation, and the A is in quotes because we could have 80 different state space representations for the same system. They would be equivalent, but they may be different. Does that make sense? And it's just because you might label your system differently than I labeled mine, and you might pack your or stack your variables in the state vector differently than I stack them in mine. And that will obviously influence the entries in our matrices describing this system. What's the size of the state vector? How big is Nevada? What is little n? What's the system order? It's 7. We go back and we count the highest powers of all of our variables. Z sub 1 was differentiated twice. Z sub 2 differentiated twice. Z sub 3 differentiated twice. And then we had a Z sub 4 differentiated once. So that leaves us with 7. We need to now have this state vector x having 7 different elements. Or it's a tall, skinny vector that's 7 elements tall and obviously 1 variable wide. It's a 7 by 1 vector. And you could write this expression down without even knowing the dimensions of your vectors, but let's now try to understand what these are. You now know the size of x, x of t, has real, that's the double vertical r, that's elements from the real numbers. It's real numbers and it's 7 elements tall. How tall is u? How many inputs do we have? We had 2. We had a v sub 1 today and a v sub 3 today. Those are stacked on top of each other. Now, we need to build up our state vector. Suppose we let x1 of t, the first component of x, be the position of the first mass. Suppose we let the second component of our state vector be the velocity of that first mass. Suppose we let the third vector equal the acceleration of that first mass. Do we need to do that? What do we need to do? We need to make sure that when we differentiate each of these state variable components once, we eventually capture the highest derivative in our system. We only need to capture z1 double prime when we differentiate x1 or x2 once. So we do not need to go that far. We do not need to define x sub 3 as the acceleration of z sub 1. Is that clear? A lot of times you go, well, how do you know when to stop? Well, you stop when if you differentiated your state variable once, you would eventually capture the highest derivative, and the highest derivative of z1 is z1 double prime. And we can get that back by differentiating x sub 2 once. So now we can start over again. We can say, oh, let's let x sub 3 be z sub 2, the position of mass 2. X sub 4, to be consistent, let's let that be the velocity of the second mass. X sub 5, you know we don't need to have the acceleration of the second mass, I hope. So now let's go to the next mass. Let's make this the third mass's displacement or position. X sub 6 is the velocity of the third mass. And finally, x sub 7 is the position of z sub 4. Why do we not need a x sub 8? Z sub 4 only has as its highest derivative z sub 4 prime, doesn't it? We don't have a z sub 4 double prime. But if that point was in fact a mass and not a massless point, then we would have an 8th order system. If you want to go home and do that, you can just replace that node between that dashpot and spring with a fourth mass, and you now have some different dynamics. You'll have to change your free body diagram. What's our input? How about I represent it differently? This is now do you see how I could really confuse you? But U could be U sub 1, U sub 2, but we're assigning it to be the two externally applied forces, and we labeled those today as V sub 1 and V sub 3. That may be confusing, but it's not intended to be. It's meant to sort of clarify what I'm meaning, or how you can sort of get lost in variables. But I don't want you to be lost. I want that to actually make sense. But just use that today. Don't try to go back, because yesterday, what did we have? We had our second input component being U sub 3. And people probably ask, where's U sub 2? I don't know where U sub 2 is. It's nowhere. But it is with us today because it's part of the input vector U. What about the output? Well, we haven't defined any outputs, have we? And it may depend on you. It may depend on your boss. It may be dependent on what you're doing. For today, let's just let it be the positions of our masses. So let's say that this, how many masses did we have? 3. So we're going to have 3 components. And let's try to be somewhat consistent. Let's say y1 is the position of mass 1, y sub 2 is the position of mass 2, and y sub 3 is the position of mass 3. And what's the dimension of that output vector? What are the exponents on this r? It's 3 by 1. This system, the way we've built it or constructed it, is 2 inputs, 3 outputs, and 7 states. And that now allows us to know exactly the dimensions of A, B, C, and D. If we wanted to write this now, we have x prime of t, which is now a 7 vector, equaling A x, so this is x prime of t in there. This is now x of t. And there's 7 variables stacked on top for x. Then we have b times our u of t. Can I get any more inconsistent? What's u? It's our input vector, and what are its dimensions? How tall is it? 2. It's 1 wide. X is 7 tall, 1 wide, and this equation needs to be dimensionally compatible. If x is 7 by 1, what's x prime? It's 7 tall, isn't it? And it's 1 wide. So how wide is A? And it's 7 rows. A is always square, our system matrix. This is our system matrix. How wide is our input matrix? It's too wide. Oh, I'm sorry. It's Friday. 2. It's too wide. 2 columns wide, isn't it? How tall is it? 7. What about our output matrix? C. What are its dimensions? How many rows? So this equation has to be dimensionally consistent. What's y? 3 by 1. That's on the left. Everything on the right has to result and end up being a 3 by 1 vector. X is 7 by 1. What times a 7 by 1 vector will give me a 3 by 1 vector? A 3 by 7 matrix. So this is 3 rows tall and 7 columns wide. How big is D dimensionally? This is our feed-forward matrix, or direct feed-through matrix, I should say. How many rows? If you've already figured out how big Y is, or how many rows C has, C and D have to be the same in their number of rows. They have to be consistent. So we have to have 3 rows in D. How many columns are in D? D now needs to be multiplied by U, and U was a vector that's 2 tall. And so D is a 3 by 2 matrix. Question? How do I know the output is 3 by 1? Anybody want to help on that? The question was, how do I know the output is 3 by 1? I just kind of pulled that out of the air, didn't I? I just said, let's make our outputs the mass positions. I could have said, I'm only interested in the position of mass 1. Then how big would Y be? Would it have 1 output, wouldn't I? Or I might say, I want to know my sensors that I can put on this system measure the velocity of mass 2 and the position of mass 1. Now what's my Y? It's 2 by 1, isn't it? I now have 2 outputs. Is that clear? I just arbitrarily said, let's let our output for this example, to give us something to play with, be the positions of our 3 masses. Now what we want to do is fill in all of these entries. We have 49 elements in A. Now this is why we learned our math multiplication tables, wasn't it? We have 14 in B, 21 in C, and 6 in D. And we have 5 minutes. Let's see if you can find the second row of A. Can you find the 7 elements that are in the second row of the A matrix? I want you to find row number 2 in the x prime equal ax plus bu formulation. If you can find that, you can find all the others. Do you need a hint? Yes? Well, if I'm interested in the second row, what's my x prime that I'm interested in? x2 prime. What's x2 prime? z1 double prime. Do you have an equation for z1 double prime? Go back to free body diagram number 1, solve it for z1 double prime, and see what results. There's the answer in the back of the book. No. So go back to your free body diagram. It's that long equation for M1 Z1 double prime. Solve that for Z1 double prime, which really divide everything by the mass, M1, and isolate Z1 double prime on the left. And that's actually equal to X sub 2 prime. Then if you have a Z1, you replace it with X1. If you have a Z1 prime, you replace it with X2. You're trying to rewrite that equation in terms of how we've labeled the state variables and the inputs. Did we all write down the same Z1 double prime equation from free body diagram number 1? And then what happens? Now you simply replace all of those Z's with the appropriate X's. And V1, that's the first externally applied input force. Where does that go in the B matrix? This coefficient 1 over M1, where does that actually live in AX plus BU? Is it B sub 2 sub 1? It's in the second row of the B, and it's in the first column because it's multiplying the first input, applied reference input. What's the A11, or I'm sorry, the A21 entry? Is it one element? Is it composed of one element? How many Z1s do we have? I see 3. So it's a busy coefficient, isn't it? The A sub 2 sub 1 element involves all of those coefficients that are multiplying Z sub 1, because Z sub 1 is X sub 1. We'll pick up at that point after the long recess, the long vacation, and we'll start somewhere. Enjoy your holiday.